Welcome everyone. Welcome to today's Digital Lunch and Learn featuring alumna Dr. Katrina Donovan. She's Chem 2010 grad. We'll give everyone a couple seconds to kind of sneak in here and get started. So, and then just so everyone knows, a couple housekeeping items before we get started. This event is being recorded and then it will be uploaded to our YouTube channel afterwards. And I'll drop that information in the chat so you guys have it if you want to view prior recordings. If you can, there's a chat function. So put, if everyone could say your class and major, where you're from, so everyone has an idea who's here, and that'd be great. And then feel free if you have questions for Kat throughout the presentation to drop them in the Q&A box or the chat box so we can see them. And I'm sure she'll answer them throughout as she gets going. So. Okay. So we'll get started. So again, please welcome our presenter, Dr. Katrina Donovan. Kat, go ahead.
Awesome. Thank you so much for that introduction. I really appreciate it. I modified the title a little bit, but what we're really going to cover today is a materials journey. I'm going to go from spinal discs all the way to 3D printed objects, and really actually go a little bit beyond that and start talking about casting and metals. So kind of just covering a wide variety of materials. I'm currently a faculty member in the Department of Materials and Metallurgical Engineering. And I would say I didn't really dress the best today. I have a t-shirt on, but I just came down from blacksmithing. So I'm a professional engineer, I guess, in the sense that I'm out at the forge. So I do apologize for that, but I'm really excited to be here and share my story with you guys today. Just a little bit of background on me. It's kind of like people know a little bit where I come from. So I graduated from high school in Bennett County in 2006, came to School of Mines, was a chem major here. I graduated in 2010. I got grubby. I kind of go through my different mascots here. From School of Mines, I went to San Jose State University where I got my master's. They were the Spartans on the right-hand side. Really good time. I learned a lot about computational work. I like getting my hands dirty. So from there, I took a year off and did a lot of STEM outreach in between my master's and my PhD. And I really found, just came back to my love of science and engineering. And so I was really going into my PhD with a lot of excitement. And I did that at Oregon State University. While at Oregon State University, I also had the chance to work at HP. I also worked at other companies, Regis, but HP, I spent 2+ years working in their 3D printing department. It was a very unique opportunity because I came in as employee number 6 in that department, and I got to watch it grow to over 200, I think, by the time I left. So it was a very unique opportunity to work within a big company, but act like a startup company. From HP, my husband, he's also a School of Mines alum. He got a position back here, and without a second's thought, we definitely came back to School of Mines. During that time, though, there wasn't quite a position for me, and I was finishing up my PhD. So my husband and I also started a consulting company, and that's Dragon Materials that you see at the bottom. So just a little bit about my background. Been in industry for a while, but I'm loving the faculty interaction right now that I get with the students. So just a little background on me. Here's an outline of our talk and kind of what we're going to cover today. This is, I will say, the only kind of gross picture that you will see in this. It's the spinal disc of a cow, actually. So it's a cow tail that I cut up. But quick outline, the first thing we're going to talk about is a case study of spinal discs, specifically humans, interest, motivation, that sort of thing. For case study number 2, I'm going to talk about 3D printing, just the background, design approach, what I did at HP and how I integrate that into my classes, my curriculum, and STEM outreach that I do. So just kind of a broad background on 3D printing. Next thing we'll cover is curriculum integration. I have a couple different case studies there. And then just current things that I'm doing that are STEAM related that I'm passionate about. And then a quick conclusion. The other picture I should just quickly note, that was it's like a brace that we printed at HP. So just kind of a demo thing to see, kind of the creativity and the creativity that can come from 3D printing. So diving quickly into the spinal disc, if we are talking about a human body, we have within our spine or our vertebrae, we have the cervical, the thoracic, the lumbar, and then the sacrum and I say this wrong every time, the cocox. And I'm really going to focus on the lumbar, but it is important to note we have 7, 12, and 5 vertebrae bones in each of those sections. The sacrum and the cocox, those are fused together, so I'm not going to focus too much on that. And even more specifically, most of my research focused on the lumbar, but I will talk a little bit about how I'm going to specifically talk about herniated disc, but I'll talk about that focused in the lumbar region. Just quickly going over these, I'm sure we're all familiar with a spinal cord. That would be, it acts like an electrical cable that travels through the spinal canal and it carries messages between our brain and our muscles. The spinal nerve is there. And then what I'm really going to focus on today is the nucleus pulposus, and you can see that cross-sectional on the image on the left-hand side where you have both the annulus fibrosus and the nucleus pulposus. The annulus fibrosus is this tough, flexible outer ring of the disc, and then the nucleus pulposus is this soft, jelly-like center of the disc. And that nucleus pulposus, it operates kind of like a shock absorber. So if you're you're somebody who drives semi-truck, you're sitting there oscillating all day long, your nucleus pulposus that will help absorb those shocks. And it's conceptually, you can think of it kind of like a jello, a very strong jello, but definitely a jello. I kind of want to dive a little bit into what we're going to be doing, just a little bit of chemistry here. So what I wanted to do was I wanted to look at replacing the nucleus pulposus, and I'll dive a little bit more into that in a minute. But what I wanted to do was essentially make a gel that could be gelled inside the spinal, the annulus fibrosus. So this idea came from a lot of STEM outreach that we were doing at the time. We were talking about gels and cross-linking. And so the project was called Gel Beads. And you can see in the image in the upper right-hand side, it says cross-linking and gelation. And this is showing an example of sodium alginate. So the sodium alginate is those black lines you see. They look like hills. That's mimicking a very long polymer. A polymer, poly meaning many, mer meaning units. So these really, really long chains, they're oftentimes thought about as it's like a spaghetti noodle. If you imagine these spaghetti noodles, well, we have essentially charged spaghetti noodles is what's happening with the sodium alginate. And most of you have probably actually eaten sodium alginate. It comes from kelp. If you've ever been through Dairy Queen or McDonald's, it's very, very frequently used as a food thickener. So you'll see it, you won't see it. You'll probably have eaten it though if you've ever grabbed a milkshake from there. Very common food item though. But anyways, these chains, you can see the negative charge, that's the blue on the upper right-hand side in that demo. They have these negative charges. So what happens with sodium alginate is if we change the salt solution, so salt water would be NaCl, it has one charge. If we change that with a calcium chloride solution, calcium has two charges. So really think about if you're gonna make a chain with one hand, that's what your sodium is. With calcium, it can grab with two hands. And that's what we're demonstrating here with those green charges. So just by changing the salt solution, we can start getting cross-linking to occur. And so this is a demo we do a lot with children at STEM Outreach. So I had been doing a lot of this activity, and herniated spinal disc came up as a topic in my PhD, and really tying, we make these gels all the time. Was there a way we can use our knowledge from these gels and how they gel to maybe doing some sort of modeling within our own spine? I never did anything within the body, but conceptually, can we even make something that would mimic the nucleus pulposus that we see within our own body? So here's kind of the two-step approach I had is the first one, I needed a model. So bovine discs, there was research done, they were found to be comparable in size to humans. Everyone's always like, well, we have human, you have humans, right? Well, to be able to test a human, I would need a human to donate, their entire, bone and nucleus pulsus and annulus fibrosis. Oddly enough, no living human wanted to donate those. So I'm not quite sure about that. I've tried in South Dakota and I've tried in Oregon. No living one wanted to donate theirs. So I had to find something else. And so that's where we got on looking at the bovine discs. And I'll show you on the bottom left-hand side, it's an image of a dissected whole and caudal, meaning tail, of the bovine disc. So the nice thing about the tail of a cow, it has a similar load to our spine. The way a cow's back is right there horizontal versus us walking vertical, they found the tail was a much better model. So what we see in the upper left-hand side, you see both the annulus fibrosis and the nucleus pulposus. So what we did is we cut out the center, which is that nucleus pulposus. We punched it out. And from there, we did some mechanical testing. I'll go into the mechanical testing a little bit, but you can see on the upper right-hand side, us testing the tail completely intact because we're gonna get slightly different properties if it's enclosed or open between, you can see in the middle there, the top and the bottom. So the bottom one was just that nucleus pulposus we were testing. So we needed a model. This was the model we were going to use. The second part was back to my STEM outreach days when I wanted to make some gels. So we started with just making hydrogels, and hydrogels are nice because you need to make sure, it's great if I make this and if it's not biocompatible with the body, there's not a lot of point in having it to some extent, right? It needs to be biocompatible. We knew that gels were biocompatible. So the gel is composed of agarose and water, so a polymer and water, and it acts as what is called a viscoelastic solid. And I'll get into that a little bit more. The cool thing about these gels is they have the ability to expel and reabsorb water. So if you were to look at these cow tails, you could tell like the annulus fibrosis, it's not, there's not a lot of water there or any sort of thing like that. So that was nice. If we look at the two different discs you see on the right-hand side, they show the 10 millimeter. The top one is just a completely, just a gel. The bottom one, what we started doing is we started putting in, it's called Sugio, but it's these foams. Not Sugio, it was Suji. And the foams are absorbent and biocompatible cellulose is what they were. So this composite is two materials you can put together. So a lot of different things that we actually have probably within your own home are composites, but the three major materials we have broadly are metals, ceramics, and polymers. And with a lot of these, the cellulose, we were able to put it into the gel. So that was kind of a nice, it gave us a little bit stronger mechanical properties, which is what we were looking for. And I'll go a little bit into the testing we did on this here. So for spinal disc testing, we're going to talk about mechanical testing. When we mechanically test, we're trying to determine a material's mechanical properties. And generally, this is independent of geometry. If you look on the left-hand side, this is probably a test most people are familiar with. Hopefully you guys will be able to see. Essentially, I have silly putty in front of me. And if I pull this is tension. And that's really what a tension test does. From that, you can get what's called an elastic modulus. There's a lot of parameters we can talk about in there, how fast we pull, how thick our sample is. There's a lot of variables, but really just want to emphasize this is tension. What we're interested in, tension is also important in the spine, but what we see in terms of like herniated discs or any sort of back pain, what we see is it often comes from compressive or torsion. So twisting, those types of movements often cause a lot of herniated discs. About 75% of people will at some point in their life have some sort of back pain. But the big test we're looking at, and I don't know if you can see very well, hopefully a little bit, but you can see we're just going to compress, and you have the two different models there. The way we're going to test this is it'll be on what's called a rheometer. And rheometer is part of this field of study called rheology, where it's a study of flow. So you can argue when we're pulling this in tension, our material's flowing, compressing it, it's now flowing out on the sides. So that's really what we're going to use to test this. And I'm going to go back one side. If you look on the far right-hand side at the bottom, you see the gel stuck to the top of this geometry, but this is a zoomed in view of what the rheometer looks like. And what the rheometer is going to do is it's set up in dynamic oscillatory. And so what it means is when I pulled this, I was just a steady pull, this thing's gonna oscillate. So it's just gonna squeeze this disc a little bit. And that would mimic something that somebody would experience in everyday life. I started with a truck driver. A truck driver, they have a lot of springs in their seat for a reason. They're bouncing. Even when we're in the car, when we're sitting, you know, just gravity, we always have some compression on our spine. That's why we should all do yoga, right? No. Joking aside, though, we do experience those compressive forces, and that's really what we're just going to focus on for this next set of data. So on the left-hand side, we have the bovine disc model. And the important thing is I said this was the model we were going to use. A good question would be, why did you choose a bovine disc to start with? Well, if we look at the humans and compare that to the bovine, we can actually see it's pretty good. If you see on the upper left-hand side, the dark red squares, that's our human data. And there's two different sets of data you see here. Probably you see the filled circles on the top and the open circles on the bottom. So the filled circles are E prime, and that E prime represents the storage, or what's called an elastic modulus. In this case, it's a compressive modulus that's denoted by the E. The E double prime would be our compressive modulus, but that we're looking at viscous or a loss modulus is what that's called. So what does that really mean? Well, if we were in person, what I would tell you is the silly putty is a great example. This is one great way to measure viscoelastic materials. Viscoelastic materials are materials that demonstrate both solid-like behavior, but also liquid-like behavior. So a lot of things you can think about is Jello, but silly putty, if you guys have ever played with this, hopefully I don't drop it and make a mess. It bounces, right? I drop it. There's this elastic response where it springs back. The other thing, I'm going to set it on my desk. You guys won't be able to see it, but I'll have my hands up. The other thing that's cool about silly putty is if I let it sit, it's going to start flowing. So it's very time dependent is what we say, but it has both these storage properties and elastic properties. And that's what this graph on the left-hand side, those two different primes are representing. Not sure if you can see, but it's nice and flat on the bottom. It's just from resting on the desk. So that silly putty's flowing. Now, let's just a little bit background on the test. Let's look at this data now. So what we see is for our human data, it had a slightly higher compressive modulus maybe than some of our bovine discs. And I plotted all the data here. So we did, I think 6 or 7. Yeah, we did 7 different trials. So there's a little bit of wiggle there, but overall, it falls relatively close to our human model, at least close enough that we can start seeing if our, you know, hydrogels and composites, if they're even close. The other thing that we did is we did 2 other tests. I'm not going to dive into those today. Just wanted to kind of focus on this a little bit. But on the right-hand side, you see for what we did. So for the hydrogels and the foams, the FG1, that's just foam gel 1, so that would be our composite. You can see all those were quite a bit higher than what we had for the bovine disc and the human data. So there was still a little bit of work we needed to do. Same test ran on both of them, but we still had some tweaking we needed to do because our material was a little bit too rigid for that. One thing I'm gonna kind of just quickly wrap up this section. So we were able to get a start on that. I kind of already told you the herniated discs, they affect about 75% of the population. The current treatment is very much reduces our functionality. So we're fusing discs instead of, you know, trying to increase mobility. And then herniation, I probably should have this slide earlier, but if you look at B, we have the weakening of the annulus fibrosus, and you see that, and you'll start having that nucleus pulposus extrude from that. And while it's doing that, it's actually putting pressure on your spinal nerve. So it induces severe back pain. Just a little bit more background there of why we were even interested in this. A lot of people suffer from this. To further wrap it up, at that time, at the time of doing this research, there was 7 undergraduates I worked with. I worked with a high school student. We presented this work at quite a few conferences, and then there was even an honor thesis that came out from this. So this was kind of like the first year of graduate school, really getting into the lab. I switched gears a little bit in grad school, and that's when I became really involved in 3D printing, and that's the direction I'm going to go now with the talk. So second case study, switching gears a little bit. On the bottom right-hand side, though, is a picture of a ship that was actually printed for MET 352 last spring. So I did not design that. I had some great students that helped with a lot of these things. So as I said, this talk is additive manufacturing, 3D printing. I do have my little HP spiel in here because I did spend time there. One of the cool things about working with HP's technology is it was an industrial scale 3D printers. A lot of the 3D printers right now, a lot of them are hobby printers, which are amazing. I have one going in the background right now, but we were working on these really big instruments. So it was pretty cool. The one in the upper left-hand side, that's just a color print. All of these though are 3D printed. We have them, hopefully some people recognize the Millennium Falcon. And then I did a post coating was another thing I worked on there. One of the super cool things though, is if you look at the bottom left-hand side, HP actually 3D printed a link, and then we used it as a chain link to hold up one of our engineers' cars. So it was kind of a fun stunt that we did. There's a video you can look up on YouTube of us doing it, but it was pretty cool to see. So let's talk a little bit about 3D printing, or what's known as additive manufacturing. I'm going to broadly talk about manufacturing first, which we're probably most familiar with is high volume. So injection molding, stamping, casting. I'm even dumping out a bucket here. One of the cool things is if you look at like the bottom of a cup, they usually have pins that you can kind of see at the top here from making a lot of those. So you heat up your material, melting metals it's used for, plastic water bottles. You're going to see lots and lots of those. This is the injection molding, is the pathway we go. But you have this open cavity, you fill it with material, and then you release it, it cools, you release it, and then you have this part. The next one, what a lot of people are probably interested in is subtractive or simple geometries, and this would be like CNC turning, drilling. The big thing to note is the steps might be different, but if we look at part one, the formative manufacturing in the simple, we have the same part at the end of this, right? Last, we have additive manufacturing. And this is 3D printing. The really beautiful thing about, each has its great thing. Formative, we got a lot of high volume. Subtractive, you can really do this well with simple geometries. Additive is great for prototyping. There's a lot of times where you're back and forth with things. And if you're wanting to have a mold for, your plastic cup and you realize, oh shucks, this is wrong, it can be quite expensive. So prototyping is a good way to go back and forth to see if you have your initial CAD or your initial design, set up correctly. So what we'll do today is we'll really focus on that. The other thing is I did want to cover is I actually will talk about some formative manufacturing that I'm actually doing within a recycling polymer processing loop. But diving a little bit more into 3D printing, we kind of have a couple big areas. Today I'm going to focus on the material extrusion, and so that's often called FDM, which FDM's fused deposition modeling. It's trademarked, so really you'll probably see it listed more as FFF, which is fused filament fabrication. With my work that I did at HP, I was in the more powder bed arenas, both for the polymers and the metals. But today, just focusing on fused filament fabrication. This is a question I get a lot by a lot of different people, and it's actually quite simple to 3D print. It sounds a lot more difficult than it is. Really, you got to start with an idea, and an idea can be a sketch. And this is one of the ships I was showing you guys. They have this ship sketched out, so just paper, sketch it out. You can then go into a CAD, which is a computer-aided design. So SolidWorks is a really common one, Autodesk. I use Fusion 360 quite a bit. Tinkercad's actually really beautiful. It's in the Autodesk family, and I'll show an example of that, but it's really great whenever I'm doing STEAM outreach with people who don't have an engineering background. That's very gooey, kind of plug and play, and it works really nice. It's also really nice for artistic, but there's a lot of different CAD softwares out there that you can use. But once you have your design, you can then put it into what's called the slicer. And the slicer operates like the way the pages of a book do. If we look at the pages of a book, each page has its own writing, right? The same thing happens when you have an object. It slices it up like pages in a book, and then it prints those in a layer by layer fashion. So from the slicer, you can then put it in the printer. Sometimes people get a little bit overwhelmed on this. And the cool thing is you can kind of skip the whole CAD process if you want, which I know there's a lot of amazing things that engineers can do in CAD, but to sometimes for people that are new to it, that can be a little bit overwhelming. If you look on the right-hand side, this is from Thingiverse. Thingiverse is this beautiful website where you can go and you can pull these CAD items off, and you can go essentially from, you don't necessarily need step 2. You can kind of go from 1 to 3, and you step over that CAD. The other thing I want to leave you guys with is my little subliminal message of CAD is cool, but really the Tinkercad's really beautiful because you can see you have the letters here. It's a very nice way to introduce, especially elementary age kids, to CAD in a friendly way. But anyways, big point here is you don't have to be the best at CAD to be able to do 3D printing. I do like this slide, just want to talk about it a little bit. This is one of the things we really kept in mind from an engineering perspective at HP, and that was fit, form, and function. Fit, we're really referring to the ability for a part or a feature to connect or join together. So on the right-hand side, you can see somebody holding that. If you spin one, all those gears interlock. So that's very important. Form just refers to the characteristics as external dimensions, weight, size, visual appearance. Form's really important if, we thought our part was going to be this big and it's this big, right? That's kind of part of it. That's an extreme example, but that's really what we're looking for here. And then function is a criteria that is met when the part performs as it's stated. So fit and form worked and it's doing what it's supposed to. So that's really important. Those are engineering specs that we really kept in mind when we were printing parts. I added my own F in here, and that's fun. I think one of the coolest things about 3D printing personally is as an engineer, we're trying to, as scientists and engineers, we're trying to optimize, we're trying to improve everyday life, whether that's a better prosthetic, a better nut to join with a bolt, whatever, a better bridge, whatever it is, we really want to improve that everyday life. So fun is part of that, definitely for me. But I think one of my favorite things out of here is actually, if you go into the top middle, you're like, what is this? If you have this same problem that I have, very simple everyday life problem, but if you have bananas in the summer, the fruit flies always come out. And we've all probably had a jar, put our apple cider vinegar in it, and then plastic over it, and you can punch holes. And so the fruit flies can smell it and go in, but then the smell is so strong they can't come out, right? At HP, we had this problem too. And so one of the engineers, you can't really tell from the angle I took the picture, but there's these little cones that go down. So the fruit flies will go in and get stuck. And then we weren't using plastic every time we wanted to change it out. So that was kind of one of my favorite things we worked on. On the left-hand side, this is a pretty standard print that you would do for 3D printing. It's just to make sure we've got good resolution, everything's lined up. You can see it is a perfect cube for the print. You can see the depth and stuff there. The other really cool thing that I got to do while I was at HP is I got to work with the interns. One of the projects we did is we 3D scanned everyone, and they got to go home with what would be called a bust of themselves. So if you look in the bottom left-hand side, that's the bust of me. We also did it with for a summer camp, and that's in the upper right-hand side. That's one of the students that we did a 3D scan on. Kind of going to step a little bit into course integration here. How do I use 3D printing now? Well, obviously, other than me just playing, which is always fun, I actually use it a lot in curriculum when I can, because it ties together so many great concepts from art to CAD to material properties. So course integration is a big one. CAD, I guess I already called it all these CAD and slicing software. You see that in the upper left-hand side. Materials, I've put a lot of different materials through my printer. Design, you can see on the bottom left-hand side. I'll go a little bit more into this later. And then we also had a competition aspect with our ships. So this is how I use it for course integration. But if we're going to be honest, this is how I really use it. I use it to entertain my children. Actually, during the pandemic, we were trying to do this design project from home. So I had my kids help me. They had a lot of fun in the creek behind our house trying to get these ships running. So
This will be for a distance of 10 feet. Go ahead and put it in, Kai. Watch, don't get wet. Go. There it goes.
I don't think the juniors in my 352 appreciated how many kids had floated their ships that they never got to cast down this little creek. It was a well-spent spring break trying to do that, trying to get all these ships ran in this tiny little creek. The original plan design was for cargo, so it kind of was interesting how all the ships came out, but there was 2 of them that we 3D printed.
This is for 10.
Whoops, get it to go to the next one. Another thing I'm pretty passionate about with 3D printing, especially polymer plastics, they fall into this area of polymers. And I'm not sure if you've ever heard of it, but there's the Pacific Gyre. It's this dead spot in the Pacific Ocean. That's where a lot of trash and garbage collects. And it's called a mountain of trash. And everyone imagines it's like Hawaii with this big mountain out. You got to imagine it's more inverted is really what happens. But this stagnation point is where all this plastic piles up, and just in an effort to reduce our footprint for sure. One of the things I really try and promote is any sort of recycling, which is very, very challenging with plastics. But here's where we're kind of at. So I'm gonna step out. I'm gonna grab some trash that comes from my 3D printer. Hopefully you guys can see this. It's just a little string. There's other supports and stuff that come, but what purpose can you argue is this going to serve, right? It's just a little string. What I can actually do is take all those miscellaneous fibers or failed prints, and I can put it in what's called a plastic shredder. This is more of a fun STEM one, where the plastic shredder, we have my high school student, she's on the bike pedaling. This bike was actually built by Jevin Meyerink. He's the co-founder of Draco, a company here. But he built the shredder. You see on the back end, you see something of this bike. It looks black and there's a white plastic container under it. That's just us shredding. You put the shredded stuff in there and it shreds it all up. So the cool thing is we can go 2 different pathways to recycle this plastic. We can go to the left, which is extrusion. And from extrusion, we could essentially be making our own filament. And the pink filament on the bottom left-hand side, that's one of the things that we could be making with it. On the right-hand side, I'm going to show some pictures of this later, but this is the injection molding. Just like I talked about earlier when I was talking about additive manufacturing, or not additive, but the manufacturing, this is a type of injection molding. And one of the cool things is, I have a bunch sitting right in front of me now, but we can use those molds and then we can start creating a little bit more artistic things. We have the stars there, the seahorse. One of the things we recently did is we went to an event. It's called SD HOSA, but it's for high school students getting opportunity in learning. But they actually used all the plastic, the leftover garbage plastic in our lab, and we made some really cool hearts from these. I think I have a fish in here too. The cool thing about these hearts is you can string them up and then you can have a necklace. So just trying to aid in that, plastic processing line. And then there's a lot of places we kind of could go, especially with the extrusion. There's research you could do where if you're, have this material and you're melting it, you can start adding things to it. So you start getting nanoparticles that you could put in to get some really interesting materials. You could add other things to modify material properties, but that's kind of its own fun research area. And then on the right-hand side is my STEM outreach or STEAM outreach side, where you can see a lot of the hearts were working really well that day, but it's pretty cool to see all the different colors that come in from really, it's garbage, I'm using garbage in quotation, but garbage materials that are coming off our printers. So it's kind of cool to just see that recycle loop. Another place I want to go with this a little bit is going from polymers to ceramics to metals. So last year about this time, it was the beginning of the pandemic. So a lot of us didn't have, we weren't in school here for sure. So one of the bummers for my junior designs, the junior metallurgical students that I have, is they had these ships and they were supposed to get to the point of casting it. We never did. We kind of got halted, and that's why my kids were creating their own competition in the creek with these. But really what we wanted to do is we wanted to have these 3D printed materials. So you can see in the top left-hand side, what we have there is we have these smaller ships. The funnel is where you would cast into it. And then that's how that was designed. But what we need to do is we need to put it into some sort of mold. And this is a plaster mold that we used. There's a lot of learning for me that went into this, but the ceramic molds, you can see I'm on the bottom left-hand side, I put them in there, but then I have to burn out my polymer. So I have this negative that I can pour into. And so that's the ceramic mold. You can see I burnt those out. And then the last phase that I did was the casting. And what I did is we just had some failed aluminums, not failed, they were intentionally broken, samples. They're dog bones I used to teach class. So I had this whole pile of essentially scrap metals, and it was an aluminum. So I was like, I'll just heat them up and see what happens. So that's what you see on the right-hand side is I've heated it up, and then in the bottom right-hand side, you can see where I've casted. And I actually have a video of me casting. So on the ground is where my mold will be, but see, it's a little bit warm. This was version 1. I wasn't smart and didn't have a funnel yet. It was like I said, a learning lesson for me. I hadn't done a lot of casting to this point. Missed the hole a little bit there too, but some of it I promise did get in. I have a couple different renditions of those. So a lot of times when I talk to people about this, they like to tell me I failed. And it was like, it didn't work the way I wanted. But the thing I really try and enforce, especially with students, it's just a first attempt in learning. I hadn't casted before. I learned a lot from that first print. I had a lot of water in there. You can go back a couple and you can see, whoops, there we go. Too far. You can see, sorry, I get excited. If you look in the bottom middle, you'll see those cracks coming out from where that burnout happened. So I just had a little bit too much water. So less cracking, hopefully. I didn't warm the mold up prior to putting, really warm metal in there. Didn't have a good funnel. Also the one, and I'll hopefully show this and you guys can see it. This is like version 2 where I had my funnel. The problem is I forgot to I didn't put on a J hook. And so all the air that's in this has to go somewhere, right? And it didn't have anywhere to go, or it's gonna, compress and you're not gonna have the bottom part of your boat, which is what happened to me here. So a lot of learning came from that. I was also using a recycled aluminum. It wasn't intended to be a casted aluminum. So, or a casting aluminum. There's, different materials that probably would have done the job better. So big thing is just going back, being redirected back to that drawing board and trying again. So my version 1, I think this was version 1 that I had, which is just a blob, on to version 2 here. So I'm doing better. What we're actually doing now is junior design. They're doing their own stuff here too. And so there's some examples of them actually prepping their molds for aluminum casting. And I kind of jumped ahead a little bit when I gave a couple curriculum examples, but I'll go a little bit more into 2 very specific cases. I kind of alluded to them a little bit, but we have STEAM and curriculum integration. So on the far left-hand side with elementary kids, I really try and motivate additive manufacturing by Legos. I think Legos can probably answer any questions we might have for or can explain it, probably any science phenomena, but really enforcing that layer by layer idea. The middle picture, we have Divine. She's one of the students that works with us. She is using a 3D pen. So a 3D pen is just like a handheld 3D printer, or a very fancy hot glue gun is another way to think about it. But she's doing some work there. I have a student on the right-hand side. He is making gel beads. Really, he got a gel blob. And then the bottom, there's one very talented student. I can't even write my name very well with those pens, but Brooklyn was able to. So first class I'm going to talk about that I teach is MET 231. It's a properties of materials class. One of the things that happened with the pandemic last spring is we kind of had to switch teaching modalities and, to make sure students are still learning at home. One of the things we ran into is phase diagrams, and I really like to relate everything we do to something in life if we can. This is an example, and I'm not going to go through it too much, but what we have here is a phase diagram. We have temperature on one axis, composition on the bottom axis, which in this case is a weight percent nickel. So as we heat up a solid metal, we'll enter a two-phase region where we have both liquid and alpha, which would be our solid region. And then we heat it up more and it becomes liquid. Depending on our composition of a material, specifically for this copper nickel phase diagram, depending on where we're at, we'll see different material properties, whether that's solid or liquid. So this was one of the things we were trying to teach in a lab setting remotely during a pandemic. So there's things I could have done in lab and recorded, but what I chose to do instead was I went all the way back. If you remember at the very beginning, I talked about how we were making these gel beads and how we had spinal discs. So what we did instead was most people had access to Jello at their house or, Jello containers. So that's what we did is we looked at gelatin. We talked about for gelatin to gel, you have to heat it. So this polymer chain unravels. And once it unravels, it can start entangling with others. And that's how it thickens and forms a gel. And then gelatin is on the bottom left-hand side. You can see that. But we actually did this, like I said, from home. Here's the recipe. I mean, you don't need to spend too much time on this. Really, I took a packet of Jello. What happens if we split it into 6 sections and modify the recipe? Some of it being we don't heat it up so that polymer chain never uncoils. Some of it, modifying essentially temperature and composition was what I allowed the students to do because that, back here, that's our phase diagram, right? Temperature, composition. And we were doing that with Jello because we had to reach a certain temperature before so that polymer chain would unfoil. Not maybe the best metal example, but it works pretty good for trying to develop a phase diagram. And so that's what we did here with this. So the idea is from textbook to everyday life. And we can see on the bottom right-hand side, we have our temperature and our composition. And so we have gels and then this gel and liquid phase or this two-phase region. And then we have just the liquid region. And I'll blow that up a little bit so you guys can see it here. On the bottom left-hand side, you can see how they're still very much in a liquid state. This is a little bit more that gel, that two-phase region where you can see some solid pieces that I've lifted up, but there's still clearly some liquid below. So gel and liquid. And then on the upper right-hand side, we're into completely gelled. So gel is also considered a viscoelastic solid. I know I talked about that a little bit earlier, but whoops. So there's just all of them together. One of my favorite slides though, is this was not, it was a pretty rough time for a lot of the students. They didn't, they got sent home. It was very much a unique time in all our lives for sure. But one of the biggest feedbacks I got was how fun this lab was. Some students didn't actually have access to Jello depending on where they're at. So I modified it so we could do eggs, but not quite as cool. This student actually came back from Easter. He said, he was like, I made a whole Jello cake. And so this was his Jello cake, which was pretty cool. This student was amazing. He actually had a clear Jello, also did really good. So just a lot of different feedback from the students. Overall, it was a pretty cool opportunity. This student went really, I kind of gave them the option of, are you going to control temperature, concentration, because it was kind of hard to do them all, but they really enjoyed the gels. This student really enjoyed the composition side. There was some pretty hard Jello, he had told me. So current and future work, I just kind of want to show you guys some of what we're doing, in the Met department, things I'm active in. In the upper left-hand side, we have Dr. West, who's the department head. He's actually, this is pre-COVID. We're outside and it's a blacksmithing event. So he's talking about just the different phases materials go through, especially blacksmithing when you heat them up, pull them out and start working with them. Bottom left-hand side is a picture we had from 3D printing camp. I'll talk about that in a minute. On the upper right-hand side, we had 7th grade girls come to campus in a normal year. This was pre-COVID, but they came and we got to do some demos with them. And then just some other outreach with the middle and the bottom right-hand side. 3D printing camp, I'm really a big part of this. This is put on by our 3D printing club on campus. They host it every year. I'm actively involved, help with the setup, tear down, come in and give some presentations. So this, the purpose of the camp is just to open the students' minds to all the different opportunities, specifically on School Minds campus. We give them tours of a lot of different facilities. They get a tour of AMP, they get a tour of camp, really getting exposed to a lot of different sides of school minds. Cool thing along with this, so this is a 3D printing summer camp for the kids. This summer, I'm also teaching a 3D printing teachers workshop. So if you know a teacher in South Dakota who wants to learn more about 3D printing, I'm actually putting this on for the first time this summer. So teachers will come to campus for 2 out of 4 weeks and we'll build a 3D printer. We'll do a whole bunch of 3D printer activities. So this should be fun. I have a link there if anyone's interested, or you can email me. Another group I'm highly involved with is STEAM Club. I started this presentation telling you guys I was out blacksmithing. If you look in the upper right-hand corner, that's my favorite hook that I made so far, but that's just blacksmithing. We learn a lot about material properties from that. The other thing on the left-hand side is we have Sierra. She's actually working on a stained glass project, which is super cool because you get in all the material properties that you see with the glass or ceramic. And then we're also integrating soldering in with that. And stained glass in itself has a great history there. On the right-hand side, my kids are there. They were also at this stained glass demo, and they had a lot of fun. The other thing is, if you go to the left, you see a lot of different colors. This was a bismuth crystal growing activity we did. And the cool thing is bismuth cools, you get these really cool crystalline structures that come out. They almost look like cities a little bit sometimes. So that one's really cool. Under that, we have a collaboration with the Blacksmithing Club. You can see a lot of swords there. This was big thing the Met Department is really good about is not just Met Department, the blacksmithing, but we highly promote the competition at TMS, our annual conference. So blacksmithing team has done very well. They've won a couple different, they've completely outright won it once and then got like best in class. And then in the right-hand side, I actually have them sitting here, and I don't know if you can see there, but we're actually gonna make these rings. They've already been 3D printed. I need to pluck them out a little bit. But from that, I'm working with the 3D print club, blacksmithing, and STEAM. And what we're gonna do is we're gonna clean those out, part of them, like half of them. We're gonna put them in a plaster and then we're gonna try and cast them. And if you can see on this, we actually could put jewels in these too once we cast them. So that's like the next STEM activity we'll be doing. I also did want to give a shout out to Dr. Travis Walker and Dr. Jonica Morrow. So Jonica is very involved with WISE, and she actually came up with this idea for essentially the operation game, but I helped a lot with the different pictures. You see, we were 3D printing different parts of it. So this is like a life-size operations game. And that just kind of wraps it up. Just in conclusion, I've kind of taken a little bit of a journey from the spinal disc to Jello to 3D printing to casting. I'm still working on the casting, but I'll get there. I hope you enjoyed the information in this presentation. My big thing is I like creating. I also enjoy characterizing a lot. So a lot of the things I do enjoy creating, but taking it to a lab and examining it is also very interesting to me. Also, just materials production's pretty cool for me as well, from soft materials to metals. My big goal, as a faculty member, whether I'm out in the community doing a STEM outreach or I'm in the classroom, really just wanting to bridge the gap between these complex materials and how we might not even know it, but we're using them in everyday life. So really just as much as we can, tying back to that everyday life. I just want to give a shout out to a lot of different people. I pulled a lot of information from these presentations over the last 6 or 7 years. So just want to thank everyone at HP. I pulled pictures from my work there. My professor's research group at OSU. And then also School of Mine students. I think I forgot to add 1 year of students here because I pulled a couple more pictures, but really so many of the students come up with really great creative ideas and I definitely can't take credit for them. They're kind enough to let me borrow their images, but there was some really great, I get the opportunity to work with some really great students. And then Walker Research Group, I do a lot of work. I collaborate with Travis Walker a lot. And then STEAM Club, Blacksmithing Club, and 3D printing. And those are my references. And does anybody have any questions? There probably were questions and I missed them in the thread.
Kat, there was a question that came in for Q&A.
Okay, so have you received any interest or orders from nuclear utilities or for a manufacturing vendor? I have not personally. I don't know if other people have. I guess the best way to say is I haven't worked directly with anyone from a nuclear utilities.
If anyone has any questions, please feel free to drop them in the Q&A section or the chat. Oh, Robert has a question. I might, if it's okay, Kat, I might pull him in.
Yeah, that's fine.
Okay.
Sorry, I didn't know how it worked. That's totally fine by me.
Robert, I'll pull you in to talk. There, oh shoot. Sorry, Robert.
The raised hand almost looks like a high five. It cracks me up every time.
Can you hear me?
Yes, I can hear you.
Finally got there. I'm a pretty old guy. And so this is over my head and mostly, but I got a question for you. Being a John Deere engineer for many years, electrical engineer, school of mines graduate, is 3D got to the point where it can create a movable assembly, or is it just strictly solid pieces that have to be mated together, just kind of like old technology?
I am gonna show you instead of answer your question because I do have good demos. 1 second. So the beauty about, and these are the ones I'm showing you are 3D printed at HP, which is a powder bed. So
Yep.
you're able to print gears. You can do this with FFF. It's HP. What we were looking at was a little bit more of an industry type of scale. We were collaborating with companies like BMW, and so it was more doing custom parts for them. So all this would come out of a print bed. And so yes, there's movable parts, there's integratable parts, there's gears. Each printing technology has its own uses and expertise, not expertise, but like specialties, excuse me. Like FFF, if we used a filament, think like a hot glue gun and tried to do something like this, there's probably support materials we're gonna have to cut out, and I'll grab. This is a failed part, but this was supposed to be part of one of the blue ships you saw. If you see all this in here, it failed on this side, but there's all this filament and extra stuff we have to take out. You'd have to do supports depending on what you were trying to make, but you might want to do supports for something that's like a gear or something similar to that. I will say 3D printing is beautiful. I'm biased. We'll start there. I'm biased. 3D printing is beautiful. Don't get me wrong. The prototyping with that, it's awesome for an R&D setting. It's not going to beat injection molding. Where it might beat, just in terms of time and, production. If we think of all the random cups that are going to come out or the plastic water bottles we drink out of, 3D printing isn't going to beat that type of injection molding. Where it might beat it is if we have a custom part. So Boeing, if you've been in one of their planes, they have those bins that they open. Well, maybe, for a majority of those bins, that handle, they're all the same size, but maybe there's that one at the front that you don't need hundreds of them, you need 10 of them. A more cost-effective route might be 3D printing, but you wouldn't want to mass produce it, if that makes sense. So more of those custom parts. A little bit beyond that I didn't really talk about. One of the projects, I don't have one in front of me, one of the projects I designed in one of my classes is I make the students design a finger splint for themselves because I can print it in a short amount of time. But the idea is if I print a finger splint that will fit my finger, my pointer finger, it's made just for my finger, where injection molding or other types of technology, that might not be the best route to go. So there's a lot of trade-offs with 3D printing. I think I more than answered your question probably, Rob, or I went on a really long tangent, one or the other.
Well, it's pretty amazing. I understand that the space station is actually doing 3D printing up there where, you know, they can fabricate a part that they don't necessarily have on site.
Oh, no, you're absolutely right. I mean, I have rolls of filament, and if you imagine you're in space and it's like, well, today I need a wrench or I need a hammer or, whatever, you don't want to be hauling that kind of stuff up. So yeah, I mean, and I don't know what it'd be. I do not, haven't had the pleasure of going up to space, but if you think about recycling lines too, maybe you need a hammer today. What does the recycling line look like if you need a wrench tomorrow? Can that be melted down, reused, and all that kind of stuff? But yeah, I do know 3D printing has been used a lot in space, or has applications there for sure.
Well, thank you very much.
You're
Good
welcome.
presentation.
Thank you. There's another one in the chat. Oh. Is there any other questions? Oh man, I see Caden in here. Caden was in one of my classes. He's gonna call me out if I didn't speak correctly.
Sorry, Kat, I was on mute. Sharon Shantos asked, what is your advice in getting young women interested in STEM?
What I'm hoping to do is there's some research out there that women tend, not females maybe, or women tend to go more toward the idea of helping people. And also there's the big thing I try and promote is the STEAM side of it. So one of the actual next projects for me is I have these hearts. You can't probably see, there's this little hole. So one of the things I was hoping to build with my polymer processing line, and I can go back to that, but I have a high school student, she's working for me right now, and she's going to be building not just hearts, but maybe it's stars, but all these different types of molds. So they'll have this recycled plastic and they'll use it. Part of it too, I think so one, having projects that appeal to them is a big part of it, I would say. And I'm hoping to do that with some of the injection molding stuff. I mean, I think they're plastic, they're arguably cheap, but they're really cool to see all the different colors in there. So I like that, but making sure we have items that, or projects, I guess probably a better way to say it, that interest women. With the blacksmithing, there's so much art in blacksmithing. A lot of the STEAM club activities we do, I keep those, I keep those where we're tying both some of that art in with the science and engineering. I think that part's important. And I think that will appeal a lot more to women. The other thing, so that's one thing, is making sure we have projects that they realize do integrate some of the things they're interested in. One, there's a lot of different pathways for women in not just women, just engineers broadly. You can be an engineer that works in a lab. You can be an engineer that works in a desk. You can be an engineer that works with people. And I think there's this idea that it's like, well, I go in and I know how to do welding or CAD, and that's all I'm going to be doing. No, like, you definitely get to plan your own adventure there. There's a lot of different professional pathways, and that's men, women, whatever. And I think probably overcoming some of those stereotypes and stigmas is important. I think the other thing too is, I try and attend events where I can, just to realize, or hopefully to help young women realize there are a lot more women out there than they probably think there are. So those are my approaches, just me staying as involved as I can with the young community and being a face in that community is my approach.
Karen asked if we could get her a copy of the presentation, because she wants to share it with fellow grads. So
Sure.
Karen, we'll get you the presentation. I'll have Kat send it over. Kaden wrote you a message.
Oh yeah. Like so good at this. Oh, thanks, Kaden. It's good to see you popping on.
If anyone, again, if you have any more questions, please feel free to pop them in chat. We'll watch for them or in the Q&A section. I'm going to also put in some upcoming events tonight we are doing, if you're interested, we're doing a women in STEM roundtable discussion. The students are submitting questions, so it could be a wide variety of topics that will be covered to our alumni, and we'll have them answered. So I'll put that in. And then next Thursday night at 5:30, we're doing a Prairie's coming in to do a wine tasting event that is online over Zoom. So it's a great way to connect with our alumni. And I'll drop that in. And as always, we're looking for feedback on our events, or if there's topics that you would like us to feature on our webinars. We do these once a month. And so just let us know. We really appreciate it. So let me find the link. It didn't save like I thought it would.
I like your background, Sarah. I'm very excited for the reunion.
Yes, and speaking of reunion, reunion will be held July 8th, 9th, and 10th, so I need to update my dates. Thursday, we will have the golf tournament in the morning, followed by summer nights downtown on Thursday night. Friday, all the events are on campus. And then Saturday, we just added in the banquet for the different groups. And I'll drop the website in the chat here so you guys can look and see. If you have any questions or anything, feel free to message us. It's $10 a person for reunion, which includes the banquet. And then if you're just going to do the golf tournament is $125. So again, thank you guys for coming. We really appreciate it. Let me do that. I'll get reunion because I just had that up there. And we hope to see you guys in July. It should be a great turnout.
Thanks, Sarah. Thank you all.